Let's start. A warm welcome to the 2026 Lise-Meitner-Lecture. My name is Ulrike Woggon and I will guide you through this evening. And first of all, I would like to thank the local organizers who really gave us this opportunity, and we are really thankful for this perfect organization and environment. It's a pleasure for me to introduce to you the president of the German Physical Society, Professor Klaus Richter, and he will give you a few welcoming words.
Yeah, good evening, everybody. Thanks, Ulrike, for the introduction. Yeah, it's great to be here again. So, let me first say hello to Michèle Heurs, of course, dear Agnes Sandner sitting over there in the third row, dear Barbara Sandow nearby, dear guests also down here and up there, also you see many faces in the first up there. And well, as president of the DPG, of the German Physical Society, I would like to warmly welcome you to our this year's Lise-Meitner-Lecture. And I will first give a few notes on the format. The Lise-Meitner lectures are a binational role model format jointly organized by the Austrian Physical Society and the German Physical Society. And that's each year, and both in Austria and in Germany. So Michèle Heurs will give a similar talk, I think, then in Vienna, probably at the end of the year in November. And but I'm rather glad that this long-standing, excellent and trusting collaboration with the Austrian Physical Society has also been reflected this year in our welcoming Austria as a country of honor, as a guest country at our spring meeting just 2 weeks ago of the Atomic Molecular Quantum Optics and Photonics section in Mainz. But coming back to the Lise-Meitner lectures, incidentally, this year's Lise-Meitner lecture marks a special anniversary. So the year 2026 marks the 100th anniversary of Lise-Meitner's first appointment as a professor. And I understood that Lise-Meitner thus became the first female professor for physics in Germany. And I think this is really remarkable, besides her later all the awards and what she did, all the achievements. Now let me say a few words about the significance of the Lise-Meitner lectures. In short, if the Lise-Meitner lecture did not already exist, then we would have to invent it. So since 2008, this annual lecture series aims to introduce outstanding female scientists to a broad audience. Among them were, during the last years, the Nobel laureates, for instance, Donna Strickland and Anna Luet. And in addition to the public and generally understandable lectures held on face-to-face events like here today, also we have this will be recorded and made available then to the public, and this exists since 2015. You can download, I think, or see at YouTube all the different lectures from 2015 on, and thereby we hope to reach a wider audience, of course. So with the Lise-Meitner lectures, we want to give young people guidance and encouragement to take an interest or to deepen interest in scientific topics. So we also want to encourage young people to have the confidence to stay in physics and science, and building on this, to pursue a career in science or also in business, of course. And to achieve this, we need outstanding role models who can inspire especially young women and provide them with guidance for their career planning later on. And I think this is not only important because physics is exciting in itself, and the career opportunities with it and with physics are very diverse and enriching. But of course, we also need engaged young scientists in physics with a view to addressing the major societal and cultural challenges. And they range these days from climate change to a sustainable energy supply and global health care and many other aspects where physics plays an important role. So I think in short we need good role models in physics more than ever, and that's why I'm also rather happy and glad that Heike Riel will be succeeding me as the president of the DPG in April, essentially in 10 days. And Heike Riel is only the second woman to head the DPG since our society was founded in 1845, so 180 years ago. And I think that's really glad that Heike will take over. She was also here at the conference during the first 2 days. And now I would like to express my great thanks to all those involved for organizing the Lise-Meitner-Lecture today here in Erlangen. However, I would also like to take the opportunity to thank in particular Barbara Sandow, because Barbara was a long-standing project manager of the Lise-Meitner Lectures in Germany. So with her outstanding commitment, Barbara Sandow helped launch this format and turned it into a flagship project for the visibility of role models in physics. For a tireless commitment to women physics and the Lise-Meitner Lectures, Barbara Sandow was also awarded with the DPG's Badge of Honor. And it's great that you already come on stage. I may also mention further that I think, Barbara, you have started this in 2008, and so for 17 years, until more or less now, or end of 2025, she has been organizing this, and now Ulrike Woggon is taking over, but we are really glad, and thank you very much again, that was great. Bitte schön. Ganz herzlichen Dank nochmal, es waren 17 Jahre, muss man sich mal klar machen. Ja. And of course, Barbara, we hope that, of course, you're not officially any longer in charge, but we of course hope that you might continue with your advice a bit in the background and expertise, and that we can still count on your expertise for the next years. Well, and now I'm very much looking forward to today's lecture by Michèle Heurs on the question, well, we probably see it here already, I don't need to read it again, and I would like to now conclude with this and hand over back to Ulrike, and she will now, I think, introduce our Lise-Meitner lecturer. Thanks again, thank you.
Yeah, the Lise-Meitner Lecture is an award, and of course for excellent contributions of women to science, and an award comes with a laudatio. So it's a pleasure for me to say a few words about the Lise-Meitner Lecture and about the today's prize winner, Michèle Heurs. The Lise-Meitner Lecture stands for recognizing and making visible the achievements of women in physics. And as said by Klaus Richter, 100 years ago, in 1926, Lise-Meitner was the first female professor in Germany. And over the past 100 years, women in physics have proven in many ways that they are not less capable than their male colleagues. But still, the proportion of female physics professors remains low. The proportion of female researchers decreases with each career level, and female scientists are often underrepresented in decision-making bodies. It's important to acknowledge role models in senior positions who can provide guidance. However, it's equally important to address and dismantle structural barriers and gender biases. It's crucial to develop an inclusive and supportive scientific community that provides a welcoming space for female scientists. And besides structural barriers such as better support for childcare and family work, in particular for fixed-term qualification pathways and mobility requirements, we have also to tackle research cultures that discourage women from remaining in the field. Lise-Meitner laureates take an active role in transforming the way science is practiced and valued, both for ourselves and for future generations of scientists. They demonstrate how diverse the career path to scientific excellence can be. Michèle Heurs is a researcher who inspires many young scientists. The awarding of the Lise-Meitner-Lecture 2026 recognizes her research, but also her commitment, which extends far beyond her actual field of research. Michèle Heurs studied physics in Hanover and did her PhD about new stabilization schemes for laser systems in gravitational wave detectors in 2004. Since 2003, she is active member of the aLIGO scientific collaboration. From 2007 to 2010, she worked as a research fellow at the University of New South Wales in Canberra, Australia, in the group of Professor Eleanor Huntington. In July 2010, Michèle took up a junior professorship at the Center for Quantum Engineering and Spacetime Research at Leibniz University, Hanover, Germany. And since December 2016, she is a professor of experimental physics at the Leibniz University, Hanover, for the field of non-classical laser interferometry. Michèle is likewise PI in the Centers of Excellence and Quantum Frontiers in Phoenix. She and her team work on the continuous measurement and stabilization of quantum optical systems exhibiting noise at or below the quantum level. They apply techniques of interferometric gravitational wave detection using laser interferometry beyond the standard quantum limit. As active member of the aLIGO collaboration for the detection of gravitational waves, she has received prestigious awards and prizes, including the Special Breakthrough Prize in Fundamental Physics, the Gruber Cosmology Prize, and the Princess of Asturias Award. Michèle Heurs received also the award for outstanding teaching in 2017, and students' evaluation of her lecture attest to her the high level of dedication and didactic skills. Furthermore, she is active in public outreach, offering inspiring public lectures and experiments. She is a true team-driving force and is committed to a healthy scientific environment. It's a great honor for us to dedicate this year's Lise-Meitner-Lecture to Professor Michèle Heurs. The title is Gravitational Wave Astronomy, vadis, and gravitational waves were for a long time purely a theoretical prediction. But in 2015, the LIGO detector researcher team was able to measure the gravitational waves emitted by two orbiting black holes. And to detect extremely small signals, precise instruments are needed. And here, the research team of Michèle Heurs comes into play, and in her talk we will be informed, I hope, in a very exciting talk about the latest developments in that field and the perspectives. So we look forward to her presentation.
Good evening, everyone, and thank you very much, Mr. Richter and Ulrike, for this kind introduction. I must admit that my ears are burning a little bit. It's really lovely to see so many interested people here, and I'm honored to be able to give this talk this evening, this lecture, and I hope it will be informative and entertaining. So and the most challenging bit will be for me to stay in 45 minutes. So let's get started without further ado. You know more than you need to know about me. Let's learn something about gravitational waves. I call this talk Gravitational Wave Astronomy, quo vadis, and I just realized that's Latin and I don't speak any Latin. But what I want to say is that we have detected gravitational waves and we are still doing that, and we have a new field of astronomy. But I would like to introduce this field by reminding you of an old field of astronomy, and that's electromagnetic astronomy, and that's amazing. I think humans probably have sat around campfires in front of caves and looked into the stars, and they probably moved away from the campfire to not be disturbed by all the light from the fire, to be able to see the stars more clearly. And then they didn't see quite this detail that you see over here. Oops, I'm sorry, I don't actually have a pointer, but that's okay. Do I? Yes, I do. They didn't quite see this detail because this is an image from the Hubble Space Telescope. And the Hubble Space Telescope, that you probably all know, when it was 25 years old, when it had its 25-year anniversary, they published this beautiful image. This is Westerland 2. It's a relatively young star cluster, and you're seeing something that is not just in the visible spectrum of light, it's also in the infrared. Electromagnetic astronomy is the type of astronomy that you probably associate with the word astronomy, looking into the sky with your eyes. And when we do that with ever more clever and sensitive instruments. Our eyes are pretty good, but then you build telescopes, and you build telescopes all the more sensitive. The better your instrument, the more information you gain from what you're observing. That makes sense, right? And when I say right, it would be so wonderful for me to see at least a few people nodding, because then I know that you're still there and also that I'm reaching you. So, because I want to make a point here, and the point is, if you build better instruments, you are able to learn more. And what does better mean? It can mean one thing, and that is more sensitive. So these are images on the left-hand side from the Hubble Space Telescope, and then from 2 instruments from the James Webb Space Telescope. And these are images of the same astrophysical object, or astronomical object, I should say. This is the Eagle Nebula, or also called the Pillars of Creation. You've probably seen this image because it's so beautiful that people like to use it as an example, just as I'm doing right now. And what you can see from left to right is the better the instrument, the more sensitive the instrument is, the better is our knowledge gain. So the more information we get. So one of our goals when we do astronomy, whatever kind, is to build more sensitive instruments to get more information, because we're curious animals, right? We want to know how the world works. So one thing we want to do is more sensitivity. Another thing that we do is we want to have a large bandwidth of information that we gather. So when I say electromagnetic astronomy, I don't just mean light, I don't just mean the rainbow, I mean everything in the electromagnetic spectrum. And when you see these images over here behind me, what you're seeing is the same object, just in different areas of the electromagnetic spectrum. So you're seeing over here in radio with the square kilometer array, in optical with ELT, X-ray, or a TeV with the Cherenkov telescope array. This is the same object, but with different colors, so to speak, in a very wide range. And more bandwidth means more information. And again, we're curious, so we need to get more information, which means more sensitive instruments, broader bandwidth. What does that have to do with gravitational waves? So far, nothing. So I have to make good on my promise. We have learned a lot about the universe from the observation in the electromagnetic spectrum, light and friends. But there are some things that are obscured from our view with our eyes or telescopes. And one of those things is we cannot look back into the very, very early universe with electromagnetic radiation. And the reason for that is that the very early universe was incredibly dense and thick and charged, and electromagnetic radiation just could not pass. So the earliest, I like to call it the baby picture of our universe, is what you can see over here in this sort of turquoisey yellow image. That is an image from the cosmic microwave background. And that's the earliest picture that we have. It's basically the baby picture of our universe in light, in microwaves. And this is about 380,000 years after what we like to call Big Bang. I'm a quantum physicist. I am actually a laser person, so I like to call that quantum fluctuations. This Big Bang, but we'll say Big Bang, 380,000 years after that, this is the baby picture of the universe. Nothing earlier exists. But obviously there was something, and we don't know what it is, because light could not come through. Gravitation was never under that restriction. Gravitation can pass through whether the environment is charged or not. We don't care. So if we want to know what happens in the very early universe, we need a different messenger. We need something that gives us information that is not limited by the fact that the universe was hot and dense and sucked up all the light. So this is where we're going to gravitation as a messenger, or gravitational waves as messengers. And I would like to now introduce you to, this is actually, my husband always laughs when I say this is a real simulation. This is indeed the visualization based on real numerical calculations of the first gravitational wave merger event that we have seen. And that event was called, or is called, GW150914, because it was measured on the 14th of September 2015. And what you're seeing over here is visualized the Schwarzschild radii of two black holes circling around each other in their sort of dance of death shortly before they merge. And you can see over here the background image is the image of the background of our observable universe, and it's kind of being sort of squished through by the fact that these two black holes are now merging to form a new black hole. So this is a binary black hole merger event. And at the end, our result is a new black hole. And it was formed out of two original black holes, but those are not identifiable anymore. They have ceased to exist. They are now one new black hole. And during this event, by the way, within this few milliseconds of fame, about 3 solar masses in terms of energy were radiated out in the form of gravitational waves. So when you convert mass to energy, a solar mass is a lot of weight, is a lot of mass, and 3 solar masses were radiated out in the form of gravitational waves in those 50 milliseconds. That was the brightest event by far during that time. Talk about 5 minutes of fame, right? So what we have over here is an incredibly interesting event, and it's not actually very unique. It was just a very strong event that we measured, and we were lucky enough to measure it when the detectors had just come online. What you're seeing over here in this number, 10 to the minus 21, is what we call strain. So what we're measuring over here is a differential length change over a baseline length. I will explain in a minute what that actually means, but what you can maybe visualize, or maybe not, I'm not sure, is the length change that we are measuring over here with our very sensitive instruments corresponds to, on the distance from here to our next star, not our next, but our next star system, Alpha Centauri, not Proxima, but Alpha Centauri, 4.3 light years. Light takes 4.3 years to travel from there. On that distance, the difference, the delta L, is the thickness of one hair, human hair. So these differential length changes are minuscule, and we can measure them. And I want to show you how. We have now, in the meantime, not just measured gravitational waves from binary black hole merger events, we've also measured 2 neutron stars merging. And over here you're seeing these white balls are supposed to be the neutron stars, the white lines that are being radiated out are gravitational waves, and after the event there was a gamma ray burst, so that's electromagnetic radiation, and then a whole range of electromagnetic radiation poured out and was observed with telescopes in the electromagnetic. 70 telescopes around the world and in space were measuring for weeks and months on end, and this is the first and so far only event of multi-messenger astronomy with gravitational waves. So we have the messenger gravitational waves, and now we also have, at the same time, electromagnetic radiation. So it was a multi-messenger event. We could hear it, and we could also see it. I've told you that we have these events, but I haven't told you what gravitational waves are. And if we want to go there, then what I want to do is try to visualize a little bit. We need to motivate ourselves that what Newton says about gravitation is fine and good, but not complete. What Einstein said in his theory of general relativity is, if I paraphrase, that masses curve space-time. So if I insert my little Earth over here into this is a 2-dimensional net supposed to visualize space-time, which is 3 dimensions of space and time. Masses curve space-time, and the bigger the mass, the deeper the dip. And you might have seen images of a black hole making like a really infinitely deep dip in space-time. And moving masses, or I should more correctly say, a non-spherically symmetric change of mass distribution will cause gravitational waves. So what you're seeing over here in this little animation is just a very simple animation of what it would look like if 2 neutron stars circled around each other. If I hop up and down, I'm going to make gravitational waves, just not very big ones. So we need really large masses to produce something that we can actually measure. And now I would like to show you, because I just postulated space-time, right? I just said space-time is being there are ripples in space-time, and that's gravitational waves. But we can't imagine space-time because it's a four-dimensional construct. And I'm just a three-dimensional being, I can't imagine that. However, if I get some help from someone over here, please, then I can show you a little model experiment, okay? We'll try that. For that, we need to switch gears. So here is my little model of space-time. And Amelie will help me to show you. This is basically just, I took a rubber glove and painted a net onto it. And you will see over here, oh, how do I do this? Wait, okay. Okay, you hold the sides. You hold the sides. Okay, I'm going to try and do this. We're going to pull and stretch and compress space-time, and then you can see what it kind of looks like when a gravitational wave passes through in this direction, okay? Okay. Good, right? We need another one, though, because, thank you so much, and I'm going to ask you to help me another time, if that's okay? Yeah? Okay. And thank you. And what we also have over here is, I have prepared another picture because I had I was on a roll. We have over here what we like to call a ring of test masses. So here's a ring-shaped object, and now we're going to look what happens if the same gravitational wave, passes through this ring of test masses, okay? Oh, thank you. Oh, that's really good. Thanks. Okay. So this is actually, I'm showing you this because when you see that gravitational waves stretch and compress space-time periodically, perpendicularly in this direction and in that direction, basically making me longer and thinner and shorter and fatter consecutively, but just a little bit, then I can hopefully motivate that a really good instrument to measure that is a Michelson interferometer. And if you have studied physics, or you were in high school physics and you remember it fondly, you might remember this device. If not, I'm happy to explain it to you because it's a really, really cool device to measure differential length changes. So the Michelson interferometer is a really simple instrument. You just need a light source. It's not going to be a bulb, it's going to be a beautiful laser, but you can build it without a laser. And this light source emits light that goes onto a beam splitter, which is a half transparent, half reflecting mirror. Then half of that light is going to go in this direction, that direction, and then that light is recombined over here at the output detector. So I'm going to split the light into two arms, and then I'm going to have interference at this port. It's called an interferometer because it has interference. We have a coherent light source. And what happens if we have equally long arm lengths, then I get the wave from one arm, the wave from the other arm. They are in phase and they will add. And that means that my output port will have a stronger amplitude, and over here it will be bright at the output. If I now shift one, we call that constructive interference. If I now shift one of the arms, one of the end mirrors, such that there is a slight difference between these two arms of n times lambda over 4, modulo lambda over 2, if I do that, then I can get the case where these two waves, they come back at the output out of phase. So every time there is a mountain, there will be a trough, and every time there is a trough from one side, there is a mountain. I should probably show this with my fingers, right? Light goes from the laser, split it up, comes back in phase, and then I have two lines in phase, two partial beams in phase. If I make one arm a little bit longer or shorter, then these two come in phase. They go in phase here, one goes a little bit further, then they come back, and then they're out of phase, and it will be dark at the output. There will be no intensity. And that's really cool because you can add light. Light plus light can make darkness. Everyone who's done physics will go, where did the light go? The light goes back to the light source. We do things about that. So this constructive and destructive interference is a really cool measure, a very simple and easy and very efficient and sensitive measure of differential length changes. And if you now remember that Amelie and I pulled that ring of test masses, you could see that the arms, if you put the arms of an interferometer into that ring of test masses, you could see that these arms over here are differentially lengthened and shortened. Does that make sense? Yeah, okay. Some people are nodding, that's good. A Michelson interferometer is a beautiful device to measure gravitational waves. It's not the only kind of device that you can use, but it's currently the only one that has proven to show gravitational waves. And I'm going to focus on this in my talk, but I want to touch back on what I said very early during the talk, and that is, I told you there is a large spectrum of electromagnetic radiation that gives us information about the universe. There is also a really large spectrum of gravitational wave radiation. And we need different types of instruments to measure those. And the ones that I'm going to be talking about are the ones here, these ground-based experiments. And you see over here that this little image over here, the schematic, is supposed to indicate a Michelson interferometer. If you want to measure events with longer wavelengths, then you have to go to lower frequencies and longer arm lengths, and then you go to space. This experiment over here is called LISA, and we don't have enough time today to talk about all of these things, but that's a topic for a whole different presentation. There are other ways of measuring gravitational waves, and there is something which is very interesting called pulsar timing arrays, where basically the pulsars in our universe are used as very exact clocks, and their time delays or time advances are used as a measure when they arrive at the Earth, are used as a measure of the stretching and compressing of space-time by gravitational waves with very low frequencies. And these pulsar timing array experiments have given some really promising results just recently. So we have knowledge of the fact that there are gravitational waves over a very wide frequency band, but today, this evening, we're just going to be focusing on ground-based gravitational wave detection. I have claimed that gravitational wave detectors should be Michelson interferometers, and they are. We currently in the world have a network of gravitational wave detectors. We have the two LIGO detectors in the US. We have the British-German gravitational wave detector GEO600 in the vicinity of Hanover. We have the Italian-French collaboration called AdVirgo in Italy. And we have a Japanese detector called Kagra. And all of these measure together. There is one under construction in India called LIGO India. And all of them look kind of similar. They are all Michelson interferometers. Their arms are kilometer scale. So the LIGO detectors have 4 kilometer long arms, AdVirgo has 3, Kagra has 3. GEO600 is a little bit smaller, 600 meters. But they all have in common that they are, at their hearts, simple Michelsons. Well, they're not that simple. We use a lot of advanced technology in order to be able to measure as sensitively as we have to. So some of the advanced technology comes from the GEO collaboration. So Germany has played an active role in making the advanced LIGO detectors and the advanced AdVirgo detector as sensitive as they are today. And some of the things that we need and that have been provided by the German-British collaboration are, for instance, the highly stable, ultra-stable, high-power laser systems. We need really, really good laser light in order to be able to build these Michelson interferometers such that they are so sensitive. Another thing that we do is very timely, is recycling. I told you that when we set our detector to the dark port where there is destructive interference and it's dark at the output, which is by the way a very good operating point, then all the light goes back to the laser. We recycle that light, we just send it back into the interferometer, and we do the same thing at the output again and recycle the signal. And we call that signal recycling and power recycling, dual recycling, and that makes our detectors even more sensitive. One more thing that we have to do is use suspended optics. If we put the mirrors of our interferometer on an optical table, and we just had it on an optical table, and then someone like me would walk by that table, the mirrors would shake. And we wouldn't be measuring gravitational waves, we would be measuring me walking around the table. We don't want that. So what we do is we suspend our mirrors as pendula. And I will show you a little experiment in a second how that works. We also need to make sure that the mirrors themselves are not contributing to the noise of our detection. We need to make sure that our suspended optics are ultra-low thermal noise. And I would really love to tell you more about thermal noise because it's such a fascinating topic, but again, that would be another hour. So we're just going to say we need to make sure that thermal noise is as low as possible. One more thing that we need to do is we need to use non-classical techniques to make our light, I like to say in German, besser als die Polizei erlaubt. So we like to make our light better than quantum mechanics would like us to have, but we're obviously not violating quantum mechanics. And this will be something I will explain to you, and it's not as mysterious as it sounds, promise. So we use something that we call squeezing, and we insert that into the output of the interferometer. And that's what makes our detectors even more sensitive. What does sensitivity mean? This curve looks confusing, but it's really not that bad. What you're seeing over here is the design sensitivity of the advanced LIGO detector with a certain set of parameters that was chosen. And this black curve over here is the envelope. What it means is this is the total noise curve. And you remember that I said we want our detectors to be as sensitive as possible, to be even better in collecting information? Which means this line over here, this black line, has to be as low as possible. But it can't be lower than the sum of all these colorful curves. And because these are uncorrelated noise sources, they add as the root of the sum of the squares of these noise sources, so the highest lying ones are the worst. Now, I did not choose these colors. This was my colleague, Rana. But you can see that the pink curve is really bad. Okay? So the pink curve is the highest lying curve. And then there's this red curve as well. And these two seem to be the ones that limit mostly. But in total, what we can say is I can only measure signals that are larger than the noise that my instrument is giving me. It's a bit like when you're at a party. You're at a party, you're talking to your friend, you're trying to exchange information, but everyone around you is really loud, and there's music playing, and there's beer bottles dropping, and you just can't hear your friend. So what you can do is you can tell your friend to speak up. You can say, make your signal bigger. Or you can tell everyone else to be quiet. You're not going to be very popular if you do that. This is signal-to-noise ratio, right? You can either make your signal bigger or you can make your noise lower. In gravitational wave detection, we do not have that freedom. We have to take the gravitational events of the strength that nature gives us. I can't tell two black holes to be a bit bigger and merge a bit more violently. The only thing I can do is make my detector as quiet as possible. Tell everyone at the party to shut up. Be quiet. Oh, what did I just do? That worked way too well. Okay, never mind. I got it. I think I got it. I thought I had it. Okay. That worked way too well. So. Moment. Ha! Okay, we got it. Experimental physics. So we need to make our signal-to-noise ratio as good as possible, because only if the signal is bigger than the noise can we actually measure something. And if we want to do that, well, we need to do certain things to our noise, right? We need to reduce every single of these colorful curves so that the black curve goes as low as possible, right? That makes sense. If we look at this curve, I told you the pink is the worst. Go figure. Also, the red's pretty bad, but also, you can see over here, this brown curve is also pretty bad at very low frequencies, right? This brown curve's pretty bad. This brown curve is seismic noise. Seismic noise doesn't usually look like that. We do a lot to reduce seismic noise, and here I would like to show you another little experiment, and I have help by the lovely Johanna, who's going to switch the camera so I can actually show you something, and this time, I need one hand. I brought a pendulum with me. It has been years when I was thinking, I'm just going to use a chain, okay? So I told you that we suspend our optics, our mirrors of our interferometer, we suspend them in order to decouple them from seismic noise. So what we do is, this is going to be this little pendant over here, okay? This little pendant over here is going to be my mirror, and it's hanging from the chain. This is a pendulum, right? This is just a harmonic oscillator. And I'm going to try to show you how this works in seismic isolation. If I move my mirrors, if my mirrors are excited at frequencies below the resonance frequency, is that working? It is. Huh? Then you can see that my mirror follows the excitation by my hand pretty much one-to-one, right? I'm moving my hand and the mirror moves exactly the same. If I excite my mirror on resonance, it's going to move, I like to say in German, wackelt wie ein Lämmerschwanz, okay? So it just moves a lot. Right? So that would not be a good frequency at which I want to measure. However, now, if I'm going to excite at frequencies a lot higher than my resonance frequency, it's actually going to, it's not a very good pendulum, but you can see that the mirror is actually not moving very much. I'm moving my hand a lot, and the mirror should not be moving very much. Can you see that? Okay. Now imagine if this was a much better pendulum, right? Very heavy mirror, very light string. Then this mirror would not, and very excitation only in the direction that I was trying to do, no jumping modes, right? This is a really cool and simple way of decoupling this, this mass from excitation by movement, which could be things shaking. It could also be the ground shaking. It could also be masses moving close by. Thank you so much, Johanna. So this seismic isolation is actually something that we use in gravitational wave detection a lot. Our mirrors are all suspended as pendula, and not just a single pendula as I showed you, but pendulum from pendulum from pendulum from pendulum. You stick from the frame, you hang a mirror, and a mass, and from that mass you hang another mass, and at the end you have your mirror, a 4-stage pendulum, and each stage gives you a suppression of 1 on f squared, which means you lose a factor of 100 over a decade in frequency. For all the experts in here, if you think in spectra, this means you lose 1 on f to the power of 8 over 1 frequency decade. Really cool. So we do that, and that's why seismic noise is not a problem. It just drops really low. So the Brown curve doesn't bother us that much. Other curves do, however. And that's why we build ultra-stable high-power laser systems. And if you go back to this curve and look over here, is laser noise even mentioned? It's not. And the reason why laser noise does not occur on this colorful bunch of graphs is because we do that really well. My colleagues build really cool laser systems, and they stabilize them so well that this doesn't even turn up. So I just wanted to give you an impression that these are not lasers that you buy off the shelf. These are laser systems that are built, custom-made, and then stabilized painstakingly. And I can't really tell you who these people are because they're wearing clean room suits. However, these are colleagues of mine installing the laser system at LIGO. So when you now move on and take a look again at this highest lying curve over here, you can see that it looks a little weird, right? This curve over here is shaped like 1 on f squared, and then it goes flat, and then it bends up again. This is quantum noise. And quantum noise it's a little weird, but it's actually quite understandable. And I'll try to explain it to you in the next few minutes. So quantum noise is the worst, but it's also really interesting. And I will take you on a little bit of a trip. And if you are a laser physicist, you will recognize all this and you can take a bit of a snooze. If you're not a laser physicist, come with me for the ride. If you think of light as an electromagnetic wave, which you can, there's wave-particle dualism, but we're going to think of it as an electromagnetic wave at the moment, then we would like to see that it is just a beautiful sinusoid. And if you don't look too closely, it really is. But if you look really closely, and you are limited by quantum mechanics, then there is some uncertainty on that sinusoid. That means that the amplitude is not just this infinitely small, thin line, it's actually a little fuzzy. And so is the phase. And this is just a consequence of quantum mechanics. It's not that we can't build better lasers. These are the best lasers. But quantum mechanics is there, and quantum mechanics tells us that there is uncertainty in both the amplitude and the phase, and in the corresponding amplitude and phase quadrature. And how does this quantum noise manifest, or this uncertainty manifest in an interferometer? Well, what it does is it manifests in the form, on the one hand side, of relative shot noise. So now I'm going to jump to the particle picture and say the light that is emitted by a laser is a little bit clumpy. That means that the photons are not evenly spaced. They arrive in bunches. And what that means is that when they hit a photodetector, it's called shot noise, or in German Schrotrauschen, because it's a bit like rain on a tin roof. Right? It doesn't arrive like an even stream. And when you look how that manifests in a gravitational wave detector and in an interferometer, then you can see it scales with certain quantities. And one of those quantities is the laser power. So I'm taking the shot noise and I'm dividing it by the total power of the laser, and then I get relative shot noise, which means that my relative shot noise in an interferometer scales with 1 on root of the laser power. If I turn the laser power up, my relative shot noise goes down. So, is that the solution? Do we just turn the laser power up? No. Because if that same laser light hits a suspended mirror, and you now know that we suspend all our mirrors as pendula, when that same laser light hits a suspended mirror, that clumpy photon stream will make that mirror shake. It will move that mirror away out of its position of equilibrium a little more or a little less. And that by itself is already, the mirror is moving, that's not too good, and it's moving in a varying way, in a fluctuating way, but also the mirror is actually hanging in the gravity field of our Earth, which means when I move a mirror out of its position of equilibrium, in the next moment it will fall back into its position of equilibrium. And now comes a really, in my opinion, fascinating point that is at the heart of quantum optomechanics. And that is the fact, if the light pushes the mirror away in one moment, and in the next moment the mirror falls back onto the light wave and pushes the light wave, It's a bit like the light shoves the mirror, and then in the next moment the mirror shoves the light. And that means that these, I'm going to use the fancy words for this, that amplitude quadrature fluctuations on the light, intensity fluctuations, are coupled into phase fluctuations, phase quadrature fluctuations actually, of the light. So the light and the mirror are coupled. This is really the fundamental point in quantum optomechanics. So this effect, this quantum radiation pressure noise, actually scales with the root of the power. So it scales conversely to relative shot noise. If I turn the power up, this gets worse, and that makes sense, right? If I have more power, the mirror is pushed away more, and the fluctuations are larger. How can I make it better? Well, I can make my mirror heavier. If I have a heavier mirror, it's going to be pushed away less, right? That makes sense. And the reason why it's actually looking like 1 on f squared is the fact that I have my mirror suspended as pendular. This is just, and I'm going to use the fancy words over here, this is the mechanical susceptibility of our mechanical suspension. So one of these is called detection noise, because when I detect, I see shot noise. And the other one is called back action noise, because the light pushes the mirror and the mirror pushes the light back. When I now look at my wonky quantum noise curve over here, the pink curve, I've tried to highlight this a little bit, then I have two branches. This is my quantum radiation pressure noise, and this is my relative shot noise. If I look at the intersection between these two, then I'm going to draw a line with 1 on f through this, and I'm going to call that the standard quantum limit of interferometry. Because if I turn down the laser power, my quantum radiation pressure noise goes down, but my relative shot noise goes up. And conversely, if I turn up the laser power, my relative shot noise goes down, but my quantum radiation pressure noise goes up. So the intersection point of these lines is moving on that orange curve. And any point under that orange curve is really hard to reach. Now, classical means broadband not reachable. So what we have to do is find some tricks. But fortunately, we have tricks. If you want to look at your coherent state, which is something that a well-behaved, well-stabilized laser emits, then you can think of, we're going to go into a bit of a deep dive now, but I will promise to take you back out of that rabbit hole. So what we're seeing over here is a visualization of a laser light, where you have a coherent excitation and you have some of this uncertainty, this fuzziness in the amplitude and in the phase. And I've shown this as I'm going to call it a red fuzzy ball. It's actually a Gaussian distribution, a rotationally symmetric Gaussian distribution. So I have an uncertainty in my amplitude quadrature and in my phase quadrature. And for a coherent state, which a well-behaved laser should emit, this uncertainty is equally spread out. But it doesn't have to be. I can also say I'm very much more interested in my phase quadrature fluctuations. Those should please be smaller. And I don't mind if my amplitude quadrature fluctuations are a little bit bigger. I pay that price. Because the only thing that Heisenberg says, the Heisenberg uncertainty relation says that the product of those two has to be larger than or equal to a certain number. And I'm going to take a page out of the book of my theory friends and say larger than or equal to 1. So I'm allowed to do that as long as the area here is not smaller than 1. So I can squeeze my uncertainty, and that's why we call this squeezing. We call it squeezing because we say we're interested in the phase quadrature fluctuations, in this case, not so much in the amplitude quadrature fluctuations. And I can build that. I mean, not just me, my colleagues and I can build that. We're very good at doing that, and we built something like this many years ago and inserted it into Geo 600. And I'm showing you this image because you can see that a squeezer, or a non-classical light source of this type, is actually a pretty complicated setup. This bench over here, this is the squeezer box. It contains 3 lasers, lots of locking loops, about 200 pieces of optics. It's not trivial to build, but it's also not rocket science. It's quantum science. And it's fun, it's really fun, and these things work beautifully. They're robust and reliable because my colleagues can do this really well. And I've shown you this also because I would like to show you to scale. This is my lovely colleague Harald Lück. He's probably about 1.95 meters tall. And you can see that this bench over here is a little more than a square meter. So you have to you have to put some work into it, but then you can build a squeezer. And if you build a squeezer, what you can do is you can make your gravitational wave detectors better. So one way we make the gravitational wave detector better is by inserting fixed quadrature squeezed light into the gravitational wave detector. That was that pink line that was going into the output. You're seeing over here the sensitivity curve of advanced Virgo in about 2019. The black curve is the sensitivity. You remember, it had to be as broadband and as deep as possible, the noise of our detector. This is the total noise. And over here, this black curve is without any squeezing. If I now put the right type of squeezing in, my relative shot noise goes down and I get this red curve. If I put the wrong type of squeezing in, amplitude quadrature squeezing, I get the blue curve. I make it worse. Do I now get the converse effect at low frequencies? I should, right? I should. I told you this should happen. And we don't really see that in this curve, so I'm showing a different curve. And we analyze, not me, but my colleagues analyzed this. And you can see over here with phase quadrature squeezed light, at high frequencies it gets better. At low frequencies, we're going to zoom in, it actually gets worse. And the same if you put the amplitude quadrature squeezed light in here, it gets worse at high frequencies, but it gets a little better at low frequencies. And this was the point where we saw, in a large scale, 3 kilometer scale interferometer, that we can make our detector better. It reduces, if you put in phase quadrature squeezed light, you reduce relative shot noise, but at the cost of increasing quantum radiation pressure noise. Now you could think to yourself, oh, well, big deal, right? You made something better, but you also made something worse. This is a case of macroscopic quantum optomechanics. And for those of you that are doing maybe a little bit of quantum optics, maybe some of you are, this should make you salivate. It should make you hungry and happy, because this is really a case where we can see something that is not expected maybe from intuition, but what we're seeing is the following. I told you that we have large suspended mirrors. This is what the mirrors actually look like. So over here you see a big chunk of quartz glass. It's a fused silica piece of glass, very transparent. We use 1064 nanometer light, near infrared from our beautiful laser systems. And you can see over here these mirrors are quite large. They're 35 centimeters in diameter, about 20 centimeters in thickness, and they weigh 42 kilograms. They're very heavy. We suspend those from glass fibers. That's a different story, fascinating. You suspend your mirrors as pendula, and then you put this phase quadrature squeezed light on it, and what happens is that your mirrors start shaking more. The fact that we squeeze our light just delicately, and we just reshuffle a couple of pairs of photons, makes our mirrors of 42 kilograms mass shake in excess, and we can measure that. This is really something that was expected, but also fascinating to observe, because it means we are seeing a macroscopic object of 42 kilograms move because we're changing the photon statistics of our light. It also meant that we had to pull more tricks out of the hat. And what we did, we meaning the entire LIGO Virgo Cargo community, 2,000 plus people, we built something called a frequency-dependent squeezer. We now squeeze just right. At high frequencies, we squeeze the phase quadrature. At low frequencies, we squeeze the amplitude quadrature. And so everything is then just right. And if you look at this, I'm going to have to speed up a little bit because I'm sure I'm going to go over time. What you can see over here is the effect of frequency-dependent squeezing. So you see again in black the LIGO Livingston and the LIGO Hanford detector, these 4 kilometer long microscopic interferometers. And if you have no squeezing, you get the two black curves for the two detectors. If you put in this type of squeezing I showed you first, this phase quadrature squeezing, you get the green curve. It gets better at high frequencies, but worse at low. Better at high, worse at low. If you put in frequency-dependent squeezing, you get the purple curves. So you get a broad band reduction in noise, which was limited by quantum noise. Now you may ask yourself, why am I not seeing the same amount of suppression of noise that I'm seeing at high frequencies also at low frequencies? And then you have to look really closely and see there's this gray curve. Those are other noise sources. And as I told you, the highest noise source, lying noise source is always the worst. I can't go below that by reducing my quantum noise. So now other people have to come and get rid of that noise. So we get this broadband increase in sensitivity. Our sensitivity curve goes lower, our noise goes lower, and we then have a better signal-to-noise ratio. So this is the point for a quick breather. I promise we will not go any deeper into quantum mechanics and quantum optics than we did. We're now back out of the rabbit hole, and I would like to take you on a quick tour of where we are and where we are going to go with gravitational wave detection. So one thing that I would like to show you is what and how we have measured so far. And then I would like to maybe summarize what we've learned from this in astrophysics, or astrophysics and cosmology. Then maybe ask ourselves, what is it that we have not yet measured? And lastly, what are we doing with all the knowledge we've gained and where are we going in the future? What are our plans? So if we ask ourselves, what have we measured so far and how much and in what way, we have measured gravitational waves emitted from binary black hole systems merging, from binary neutron stars merging, in one case with the simultaneous emission of electromagnetic radiation. We've also measured that black holes sometimes swallow neutron stars. Those are the types of events that we have measured. And we have measured more than 200 confirmed events, and we have in total about 391 candidate events. And what you see over here in this colorful graph is the observation runs. So you can imagine that a gravitational wave detector is a complicated system made up out of many different subsystems. And when you want to observe, you want that your detector is online all the time, measuring constantly. And that takes a lot of work because the gravitational wave detector has to be maintained. But you try to run consecutively for many weeks and months on end. And then at some point you go, now we have to fix stuff. Now we have to repair things, we want to improve certain subsystems, and then you take the detector offline and you take a break. So every time you measure for a long time, we call that an observation run. Beobachtungskampagne, Messkampagne. We call it an observation run. And then between those runs, observation run 1, 2, 3A, 3B, 4A, 4B, 4C, there are long stretches of time in which we didn't measure because we were working to improve our detectors. But if you sum all of those up, if you just say all the measurement times concatenated, you can see over here that we measured a lot of events over that time. And the events that we measured are shown in this graph over here. We call that masses in the solar graveyard. On the x-axis, nothing sensible. This is just an aesthetic representation. It looks a bit like a bird, right? This is an aesthetic representation of all the events that have been measured. And over here you see solar masses. So this is the mass of our sun is a unit that astronomers like to use to quantify because we can sort of maybe a little bit imagine how big our sun is. And as a standard, solar mass. So when you look over here, the things that we have measured are mergers of two black holes. These are the two blue circles merging. We have measured the mergers of two neutron stars, which can then, called a binary neutron star, which can lead to either a very heavy neutron star or a very light black hole. And we have also measured when black holes swallow neutron stars. So if I go back from this, you can see over here, a blue circle and another blue circle form another blue circle, so two black holes are merging to form a new black hole. Or a neutron star and a neutron star merge to form either a very light black hole or a very heavy neutron star. Or a neutron star and a black hole merge to form a slightly heavier black hole. Those are the three types of events that we have measured, but we've measured them multiple times. So now we don't just say gravitational wave detection, we now say gravitational wave astronomy, because from all these events we can deduce a lot. And the things that we can deduce, the things that we have learned from gravitational wave events, are multiple. This is not an exhaustive list. I've just shown you the highlights. At least I tried to show you the highlights. We now know that binary systems of black holes exist. We kind of knew that beforehand, but now we can measure them. And they do merge sometimes. And not as rarely as you would imagine. It's quite often. We know now that there are so-called Kerr black holes. Black holes are very simple objects. They have mass, they can spin, they can have rotation, and they could maybe also have charge. We now know that there are indeed spinning black holes. And we know that from mergers of black holes, where when they merge and they have been spinning and they spin with their axes under misalignment, they actually show in the signal precession. We can actually measure that. We also have measured black holes with unexpected masses. So intermediate mass black holes events have been measured. We know that there are also compact objects in the mass gap. So when I said it merges and forms either a very light black hole or a very heavy neutron star, that's weird. We know that these exist now. We have seen mergers of two neutron stars. We now know from that merger, from this GW 170817, we know that at least a large fraction of the heavy elements that exist come from these binary neutron star mergers. And we also have seen that some of our gamma ray bursts actually come from these types of events. We can localize gravitational wave sources because we have multiple detectors. And a bit like with GPS, when you have multiple satellites, you have better triangulation of where you are. If we have multiple detectors online, we can pinpoint quite well on the sky where the signal came from. We also have confirmed that gravitational waves do propagate with the speed of light. So we have a different messenger. Gravitational waves are something completely different. They're quadrupole waves, but they still propagate at the speed of light. And we have also confirmed general relativity once again. And we have measured the Hubble constant, which tells us something about the expansion of our universe, with an alternative measurement. We call that a standard siren. So now you might ask yourself, what have we not learned yet and what have we not yet measured? I told you we have binary neutron star mergers, binary black hole mergers, and black holes eating neutron stars. We have not measured supernovae. When a large star, a large enough star, reaches the end of its life, it can go supernova. And if that happens, basically the star explodes, and it should make a noise. However, not a noise that we can hear, because as you know, at least latest after you've watched the Alien movie, in space no one can hear you scream. So we should be able to measure that in gravitational waves, but we have not yet. We've also not measured whether neutron stars might have little bumps on them. So neutron stars are compact objects. It would be kind of weird if they were rotationally perfectly symmetric, but it seems so far that on this object that has about a diameter of maybe 20 kilometers, the little bumps on that are less than on the millimeter scale. So mountains on a neutron star must be very, very low, very, very low. Because if they weren't, we would measure gravitational waves from them. And we have also not measured anything so far that we could not explain. There was no fingerprint on the signal stream that we have not been able to explain yet. So we have not measured unknowns, and the unknowns are actually the most interesting thing. I already told you that we've been measuring in observation runs. So measure for a long time, then take a break. Here's what you can see. You can see over here that we started with observation run 1, and right at the beginning of that, we measured this first gravitational wave event. And then we took a break, and then there was 02, 03, 04. We're now, at this moment in time, in a phase where we're upgrading again. And in reality, we were supposed to take a longer break to do a lot of upgrades, to then move on to 05. However, because the Vera-Rubin telescope went online, and we measured a little bit at the end of 04 for 2 weeks in unison with Vera-Rubin, it would be a shame if we didn't keep measuring, and so we have inserted about maybe half a year intermediate run, which will start at the end of this year. And when we've finished with that, then we'll do a large upgrade, and we'll hopefully go into observation run 5, but all of these things are still under consideration, because things change. Post 05, we will have the next generation of detectors. And we have that next generation of detectors because, as I said, we want to be more sensitive and more broadband. And so what you're seeing over here is the sensitivity curves of the LIGO detectors over these observation runs, and you can see every time we improved, our noise got lower, our sensitivity got higher. In 05, we hope to be at this yellow line. When we go to the next generation of detectors, we want to have an improvement of at least a factor of 10. So the Cosmic Explorer project that has been proposed for the US and the Einstein Telescope fulfill that requirement. They are much more sensitive. What that means, a factor of 10 might not sound so much. Whether I have 10 euros in my pocket or 100 euros in my pocket, actually that does make a bit of a difference. But it's actually much more dramatic when you have gravitational wave detection, because if you look at this animation over here, you can see that the initial LIGO range was about 15 megaparsec. Then if we move on to the next, you can see that the observation range got larger for 02, where it was nearly 100 megaparsec, 03, 135, 04, we're at 170 megaparsec. That's the astrophysical reach that we actually have with gravitational wave detectors now, if we were measuring at this moment in time. If we get a factor of 10 more in sensitivity, we can measure 10 times further in each direction, so in this, and this direction. And that gives you 1,000-fold larger volume. And that gives you a lot more information. And as I told you early on, I'm a curious person, I want more information. So what we want to do is measure more sensitively in order to detect more. And what we do for that is we go to the next generation. Thank you. As you can tell, I'm a nerd, and I like Star Trek. So the next generation actually means we're going to move on to the next generation of gravitational wave detectors, and we will have LISA, the space-borne gravitational wave detector in space, 2.5 million kilometers, 3 satellites in a heliocentric orbit trailing the Earth, and a talk for a different evening. But we also have these detectors, this Cosmic Explorer in the US, and the Einstein Telescope somewhere in Europe, and maybe even a detector in Australia. I've not given up hope. I would like to focus on the Einstein Telescope because this is a European detector, and we're in Europe, and I'm a convinced European, so I'd like to tell you a bit more about this. It might look something like this. It will be a European project, that much is clear, and I'm very happy that it is, and I hope for all the positive effects that it will have, not just for science, but also for society and for politics. And it will be, and now please bear with me, it will be a future, triangular, or maybe 2L-shaped, underground gravitational wave observatory at 200 to 300 meters depth, with 10 or 15 kilometer long arms somewhere in Europe. There's a lot of unknowns in here, and that's okay. The unknowns, configuration and topology are not clear yet, location is also still undecided. I'll briefly touch on that. You could either build L-shaped detectors as we have so far, and you could build 2 and then rotate them, build one like this and build the other one somewhere else under 45 degrees, or you could build a triangle. And that triangle is made up out of 3 V's. And trust me, you can basically calculate one from the other. They're equivalent. There are fans of one topology, there are fans of the other topology. We have not yet decided which topology we're going to choose. That decision is still outstanding. And it's not because people are not doing their homework. That homework is done. It's just a multi-dimensional optimization problem, and it's not easy to choose. It's not like, it's a bit like asking, do you prefer chocolate ice cream or raspberry ice cream? Both are good. The same about location. We have 3 probably really well-suited candidate sites, and that's good. If we have 3 well-suited candidate sites, great, then we can choose. However, these candidate sites, the investigations have not yet been finished. We still have time to finish them. We need to hurry up, but we are on our way. There is a candidate site in Sardinia, there's a candidate site in the triangle between Belgium, the Netherlands, and North Rhine-Westphalia, and there's a candidate site in Lusatia, which is in the far southeast of Germany. So the site's investigations have not yet been completed, so the decision on site locations is still outstanding. It depends on whether we want 2 L's or a triangle. We're going to get there. Stay tuned. One thing that, however, we do have in common, whether we choose a triangle or 2 L's, is that this sensitivity over here of the Einstein Telescope is by virtue of something very clever, and that is the xylophone design. What it means is we're going to split up the technological challenges that we have in our detector into a higher frequency and a lower frequency part. We're going to build co-located interferometers that will have vastly different technology operating in them to solve these problems or challenges individually. So we're going to split that up, and then we have a low-frequency detector and a high-frequency detector. And if you put these 2 next to each other, you get this weird-looking red curve. What it results in is, as I promised, there's more than a factor of 10 better sensitivity as opposed to the current 2nd generation of detectors. We're going to go from the blue curve, which we now basically reached, to that red curve, which means factor of 10 or maybe even a factor of 100 or more at low frequencies. And that results in a vastly increased astrophysical reach. As I promised, you want to look deeper into the universe, and you can. This is advanced LIGO reach in redshift, and this will be Cosmic Explorer and the Einstein Telescope, going back to redshift of 100 for certain normalized events. And one way we're going to be doing this is by all pulling together and solving the technological challenges, and maybe also the political challenges and the financing challenges that will come with wanting to build something so complex. One very cool development that has happened in the last years is that we have a new center in Germany called the German Center for Astrophysics, the Deutsche Zentrum für Astrophysik, DZA. And this German Center for Astrophysics will help us to achieve some of these goals by being a national center that can help facilitate such national planning. And I would like to just briefly introduce it to you, so if you ever come across it, you've heard it before. There will be 2 locations of the German Center for Astrophysics, one being the campus in Görlitz and the other being the so-called low seismic lab in the triangle between Hoyerswerda, Kamenz and Bautzen, which is not very far from Dresden. The challenges that we want to tackle with the DZA are astronomy, technology development and computer sciences, and I'm going to rush a little bit, because I can see that people have to leave. And that is one of the things that we want to do, and I think I teased this a little bit earlier, is we need heavier mirrors in order to have them less sensitive to quantum radiation pressure noise. If we have heavier mirrors, then we're able to be less susceptible to quantum radiation pressure noise. We need, for these new detectors, for the ET low frequency, we need mirrors made out of silicon, not quartz glass, silicon. Silicon comes at a certain size these days, and the purity that we need it bigger. And that cannot be done yet. So that's one thing that the DZA is working on. And once we have that, and all of the other challenges, many of them, that I'm not going to list over here, have been tackled, then there is a lot more science that we can do with the Einstein Telescope. I'm aware of the fact that you're not supposed to show slides like this because everyone starts reading, but I have uploaded the files, or actually Johannes has uploaded the files, and if you want to see this list, you can actually, I would actually recommend very much that you have a look at this beautiful book called The Science of the Einstein Telescope, also sometimes called the Blue Book. It's about 880 pages, more than 200 of which are references. There's nearly 6,000 references. Go figure. A lot of science to be done. And you can see over here we can do a lot of astrophysics and fundamental physics. We can learn about dark matter and dark energy. We can probably detect new astrophysical sources. We can measure back to the dark ages of the universe, measure all binary black hole mergers, lots of neutron star mergers, and maybe the unexpected, because Einstein Telescope is going to be a discovery machine. We'll measure things that we were not expecting, and I'm most excited about those. But if you ask me what my favorite source is that I would like to hear within my lifetime, it would be this. And you probably can't hear this because I did not turn on the music. Okay, this is a bit underwhelming. This animation, which really is only an animation, is what an artist thinks a supernova would look like, and the result is going to be the Crab Nebula, which is a supernova remnant. I'm absolutely sure that's not what a gravitational wave will sound like. It's probably going to sound like this. And this is not an animation. That was actually a simulation of a supernova in gravitational waves. So stay tuned, and I thank you for your attention.